Hey everybody, it's Mr. G. Just what we're going to be doing is a quick little review for test 1 on Tech 101. Test 1 review. So far we have covered quite a bit in this course. We started off talking about things like scientific notation, and then we moved on to engineering notation. And then we started talking about prefixes. So for this course, the ones that you're responsible for, there was 10 to the 0, 10 to the 3, 10 to the 6, 10 to the 9, 10 to the 12, and then 10 to the minus 3, 10 to the minus 6, 10 to the minus 9, and 10 to the minus 12. And that was the base unit, kilo, mega, giga, tera, milli, micro, nano, pico. And then how to go back and forth between each one. So know what scientific notation looks like, know what engineering notation looks like, as well as the corresponding prefixes. From there, we moved on to the basics of electricity, and we looked at voltage and current and resistance. So for voltage, that's that potential energy that gives those electrons enough energy to leave the atom and flow freely through the material. And that's what ends up being current. So remember, current, we're DC current, so DC stands for direct current, which means current is flowing in one direction and one direction only. And there was two types of DC current. There was what we know as conventional and electron flow. So conventional is positive to negative, whereas electron flow is negative to positive. The unit for current is the amp. The unit for voltage is the volt. Amp, we talked about a unit of charge being a very large group of electrons. So 6.24 times 10 to the 18th electrons, making up 1 coulomb or 1 unit of charge. And 1 coulomb per second is 1 amp of current flow. We also talked about resistance. Resistance is the opposition to current flow, and the unit is the ohm, Greek letter omega. And then we talked about what is a resistor. So the resistor is the component that resists the flow of current. So if you have voltage pushing the current along, resistance is what's holding it back. So the resistance is the opposition to current flow. And then we talked about an actual resistor. There were two types of resistors that we talked about in class. Specifically, there was the standard 4-band resistor, and then there was the precision 5-band resistor. So with the 4-band resistor, there were 4 bands of color. First one is the first digit. Second one is the second digit. Third one is what's known as the multiplier. And the fourth one was the tolerance. With a 5-band resistor, also known as a precision resistor, we have 1, 2, 3, 4, and 5 bands, where we have first digit, second digit, now we have a third digit, so one more digit of accuracy. Then we have the multiplier, and then we have the tolerance. From there, we went on and we actually looked at the resistor color code and figured out how to actually determine values of resistor based on the color code. And the color code looked like this. And we had learned this little nursery rhyme. So this was black and brown and red, orange, yellow, green, blue, violet, gray, and white. And the nursery rhyme was bad beer rots our young guts, but vodka goes well. Then we had tolerances, and the tolerance colors for the 4-band resistor that we were concentrating on, we had red at 2%, so plus or minus 2%, and then there was gold at plus or minus 5%, and then we had silver at plus or minus 10%. And if there was no 4th band at all with that resistor, so none at all, those were one of the old school 20% tolerances. Then, because of the manufacturing process being so much improved, we can end up with the precision resistors now. And the precision resistors also add to the ability to have tighter tolerances. So we had red at plus or minus 2%. Then we had brown at plus or minus 1%. And then from there, we could have 0.5%, and that would be green. And then 0.25% at blue, and finally violet at plus or minus 0.1% tolerance. Then we figured out that we needed to be able to make values less than 10 and values less than 100. So in order to do that, we introduced 2 new multipliers. So 10 to the minus 1 is gold, and 10 to the minus 2 is silver on the multiplier. So what that means is if we had colors, let's say brown, red, and then gold, so we would actually do times 10 to the minus 1. So what that does is it moves the decimal point. We end up with 1.2 ohms. So let's just quickly do a couple of examples of resistors. And there are plenty of them in the textbook, and we've done lots of them in class. But let's just take a really quick look. If I had a 4-band resistor, 1, 2, 3, and 4, and the colors were brown, red, gold. So what we would do is we would go to our resistor color code. Brown is the first digit, so that's going to be a number 1. Red is next digit, that's a 2. Red as a multiplier means times 10 to the 2, and gold tolerance is plus or minus 5%. So this works out to be 1200 ohms plus or minus 5%, which translates to 1.2 kilo ohms at plus or minus 5%. If we had a 5-band resistor, and let's say the colors were orange, 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 red, and then brown. So orange, 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 and red, tolerance brown. So that would be digit, 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 and then the multiplier. So digit is going to be orange is 3, orange is 3, orange is 3. Those are 3 digits. Multiplier times 10 to the red, which is 2, and plus or minus brown is 1%. So that works out to be 33300 plus or minus 10, plus or minus 1%. And that works out to be 33.3 kilo ohms plus or minus 10%. So that is for the 5-band resistor. At that point, we went and looked at the most important relationship that there is in electronics, and that is Ohm's law. So Ohm's law is the relationship between voltage, current, and resistance, and that relationship is represented mathematically as voltage is equal to current times resistance. So this is the baseline formula for pretty much everything that follows in electronics. So then we started looking at some series circuits. So series circuits we had a voltage total R1, R2, and R3. How do we know these things are in a series? Most important thing is because they share the same current. So what that means is, if I was to track the current as it leaves the source, that current will flow through that resistor, flow through that resistor, and flow through that resistor on its way back. So therefore, all components share the same current. We talked about a bunch of rules that we use for series circuits. So because everything shares the same current, I total is equal to I1, which is equal to I2, which is equal to I3, etc., etc., etc. So any current through any resistor is the same as the total. We looked at finding total resistance in a series circuit is R1 plus R2 plus R3, etc., etc., etc. We know that Ohm's law works. We also know that we have this thing where each resistor drops a bit of voltage as the current goes through, according to Ohm's law. So the voltage drop across each resistor. So if you add up the voltage across R1 plus the voltage across R2 plus the voltage across R3, etc., 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 you get the total voltage. And that was Kirchhoff's voltage law for series circuits. And again, Kirchhoff's voltage law for series circuits states that all of the individual voltage drops add up to the total. And then we were able to derive what's known as the voltage divider law. And the voltage divider law says that I can find the voltage across any resistor if I know the total voltage, the value of that resistor, the total resistance of the network. And there you go. And those were the rules that we had dealt with series circuits. One of the other things that we added at that point was power. So power in resistors. P is equal to voltage times current. P was also equal to voltage squared divided by resistance. P was also equal to I squared times resistance. The unit was the watt. And that is the electrical energy being dissipated as heat in a resistor. So we looked at that at this point in time as well. And then we moved on to parallel circuits. And with parallel circuits, the circuit kind of looked like this. V total, R1, R2, R3. So with a parallel circuit, basically what we're dealing with is identifying this as a parallel circuit, which means that unlike a series circuit where they share the same current, a parallel circuit shares the same voltage. So that means all components share the same voltage. So that means voltage total is equal to the voltage across R1, which is equal to the voltage across R2, which is equal to the voltage across R3, etc., etc., etc. We also know that Ohm's law works, because Ohm's law works all the time. We also derived the idea that we have branch currents that all originate from the total. So the total current is equal to the sum of all of the individual branch currents. So IR1 plus IR2 plus IR3 is equal to I total, and that was Kirchhoff's current law for parallel circuits. So Kirchhoff's current law for parallel circuits states that all of the individual branch currents must add up to the total. We also ended up with a formula that looked like this. So the current through any individual resistor is equal to the total current, total resistance over that individual resistor, and this was known as the current divider law. Speaking of R total, we had worked out that R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3, etc., etc., etc. And that is the main formula that we use for solving any total resistance in any parallel circuit. We also talked about two shortcuts. So two shortcut formulas. The first one for R total was equal to the product over the sum. So this would be R1 times R2 divided by R1 plus R2. And this works if you only have two resistors. So that formula can be used if you have two resistors in parallel. There's also this one. R total is equal to the value of one resistor divided by the number of resistors you have. And this formula can be used when all resistors are the same value. So there was two shortcut formulas that we added to our list. So we had all sharing the same voltage. Ohm's law always works. I total is equal to the sum of all the individual branches. That's Kirchhoff's current law. We have the current divider law, which states that if we wanted to calculate the individual current in a branch, we can do so by knowing the total current and the ratio of R total to Rx. And then we had the three formulas for calculating the resistance, total resistance of a circuit. We also discussed conductance, G. It was conductance. And conductance is 1 over R. The unit was a Siemens. Used to be called the mho. So basically, conductance was the ability for a resistor to pass some circuit or some current, whereas resistance is the ability to hold some back. So the two things are completely opposite. All right, so here's our formula sheet. So that formula sheet is going to be attached to your tests. And on the formula sheet, you've got Ohm's law, you got the power formulas, voltage divider, current divider, total power. Got total resistance for series, total resistance for parallel, and for parallel. And the rest of the formulas we haven't got to yet. So what we're going to do is a couple of really quick, simple examples. So first there's going to be series circuit. Let's solve a quick series circuit. So power supply, and we'll call that 12 volts. We'll say R1 is 1K, R2 is 2K, R3 is 3K, R4 is 4K. And what we're going to do is we're going to solve for all of the unknowns. So the voltage across R1, the voltage across R2, voltage across R3, voltage across R4. Then we're going to get the current through R1, current through R2, current through R3, current through R4. And then we're going to do our powers. Power dissipation of R1, power dissipation of R2, power dissipation of R3 and R4. We're also going to get total power. We're going to find total current and total resistance. So first of all, we have to identify this circuit. So from our rules and laws that we know, since power or the electricity is going to come up through this way, the current is going to flow through all of those resistors on its way back. So therefore, all resistors are sharing the same current. So that means that this is a series circuit. So what we want to do first is calculate our total. So our total from our formula over here, our total is R1 plus R2 plus R3 plus R4. So this is 1K plus 2K plus 3K plus 4K. So that is going to give us 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 kiloohms. So now we can use Ohm's law. Ohm's law says V total over R total is equal to I total. So we can take our calculator and we can say 12 volts divided by 10K. So that's 10,000 ohms equals 0.0012 amps. And that is 1.2 milliamps. So 1.2 milliamps. So since all of the currents are the same, they are all equal to 1.2 milliamps. 1.2 milliamps. And that is because this is a series circuit. 1.2 milliamps. Now, voltage. Voltage is current times resistance. So the current through R1 times the resistance of R1, this is going to be 1K times 1.2 milliamps, which gives us 1.2 volts. Next one, 2K times 1.2 milliamps is going to give us 2.4 volts. 3K times 1.2 milliamps is going to give us 3.6 volts, and 4K is going to give us 4.8 volts. Now, how do we know these numbers are correct? Well, we can go ahead and we can apply Kirchhoff's so down here, Kirchhoff's voltage law for a series circuit. If we add up all of these, we should get somewhere near the total. So we're going to do 1.2 plus 2.4 plus 3.6 plus 4.8 equals 12 volts. So 12 volts matches 12 volts. So those numbers look good. What's next is calculating the total, or the powers and the total power. So power of R1, we have 3 different formulas we could use for calculating power, because we have the voltage, we have the current, and we know the resistance. We could take any formula, so we might as well just take the simple one of voltage times current. So voltage, 1.2 times 1.2. So 1.2 volts times 1.2 milliamps of current gives us 1.44 milliwatts of power. The next one is 2.4 times 1.2 milliamps equals 2.88 milliwatts. 2.88 milliwatts. The next one, 3.6 volts times 1.2 milli is 4.32 milliwatts. The last one is 4.8 volts times 1.2 milliamps equals 5.76 milliwatts. Now, we're going to add all of those up to give us the total. So that's 1.44 milliwatts plus 2.88 milliwatts plus 4.32 milliwatts plus 5.76 milliwatts, giving us a total of 14.4 milliwatts of power. Now, if we want to make sure that all of our numbers are correct, what we're going to do is we're going to find power total using I total and V total. So I total is 1.2 milliamps times V total was 12, therefore 14.4 milliwatts. So this value and this value are the same. We came up 2 different ways to get the same number, so chances are our math is correct. So that's solving a simple series circuit. Let's do the same thing for a parallel circuit. Remember, there's lots of examples. You can go back and watch the video lessons. There are examples on there as well. So for a parallel circuit, voltage applied is going to be, we'll try 24 volts. We got 1K, 2K, and 3K, and this is going to be R1, R2, and R3. So what we're going to do is we're going to find the voltage across R1, the voltage across R2, the voltage across R3. We're going to find the current through R1, the current through R2, and the current through R3. And then we're going to find the power dissipation of R1, power dissipation of R2, power dissipation of R3. And then we're going to find our I total, R total, and we are going to find power total as well. So first thing is we have to verify that this indeed is a parallel circuit. So the voltage here is across this resistor, is across this one, and is across this one. So they all share the same power supply. They all go directly across the power supply. So therefore, all of the voltages are the same. So if the power supply is 24 volts, the voltage across R1 is 24 volts. Voltage across R2, 24 and 24. I can now use Ohm's law. 24 volts divided by 1K gives me the current. So that's 24 milliamps. 24 volts divided by 2K, 12 milliamps. 24 volts divided by 3K, 8 milliamps. I can now add up all of those to get my I total, because according to Kirchhoff's current law for parallel circuits, all of the branch currents, so that's this one and this one and this one, all add up to be the total. So that is 44 milliamps. Because I have voltage, current, and the value of resistance, it makes it easy to calculate power. I can use any of the power formulas on our formula sheet. So in this case, let's just do this one. Power is equal to voltage squared divided by resistance. So voltage is 24 volts squared divided by 1K. So that's divided by 1,000 equals, this is 576 milliwatts. 24 volts squared divided by 2K equals 288 milliwatts. 24 volts squared divided by 3K. So 192 milliwatts. Okay, so now what we're going to do is we're just going to check for the total power. So we're going to add all of those up. And we're going to get 576 plus 288 plus 192 gives us 1,056 milliwatts of power, or 1.056 watts of power. Now we need to figure out R total. Now R total, we can use the total current, so we can use Ohm's law, and we can say 24 volts divided by 44 milliamps. So 24 divided by 44, exponent 3, the negative, equals 545 ohms. Now, does that make sense? Well, it should, because in a parallel circuit, the total resistance is always going to be smaller than the smallest individual branch resistance. So what we're going to do is we're going to verify that answer by using the 1 over R1 plus 1 over R2 plus 1 over R3 formula for R total. And that becomes 1 over 1K plus 1 over 2K plus 1 over 3K. And when you enter that into a calculator, again, everybody's calculator is different, so make sure you understand your own calculator. My calculator is 1 exponent 3, so that's the 1K part. 1 over plus 2K, 1 over, plus 3K, 1 over, equals, and then got to do the final 1 over, 545. So 545 ohms matches 545 ohms. Now we can double check this value. So we can say power total is V total squared divided by R total, or any of the other power formulas we want to use. So V total is 24 volts. 24 volts squared divided by R total, we just figured out, is 545, equals 1.05 watts. And they match. So when all of our answers are matching, pretty good chance that we calculated this correctly. So there's examples in the textbook you can do. There is the videos, the lessons with the extra examples there. But I hope this helps. So again, this was Tech 101 Test 1 review. Good luck on the test, everybody. Take care.